Next exercise 61. So here we are given a finite group G and a subgroup H of G and an element small g belonging to G such that n is the smallest positive integer for which this power of G to the power n is an element of H. Under these conditions we have to prove that n divides the order of this element G. So we start the solution like this. By the division algorithm, if we divide this integer by n, then there will be a unique quotient and a unique remainder. So there exist unique integers Q and R such that the order of G is Qn plus R, where R is non-negative and less than n. Now, if we look at this power of G to the power R, then R can be replaced by order of G minus Q of n from this equation. Minus Qn, which by the rules of exponent is equal to G to the power order of G to the power n whole to the power minus Q. Now G to the power order of G is identity, so we end up with this. Now since G to the power n belongs to H, so this integral power of G to the power n also belongs to H because H is a subgroup. Now look at the situation. This integral power of G belongs to H, where R is a non-negative integer less than n. But according to the minimal nature of n, no smaller positive integer will give us a power of G that will belong to H. So that means here R cannot be positive, because if R is positive, then this statement that G to the power R belongs to H contradicts the minimality of n. So that's why R cannot be positive, so R has to be equal to 0. If R is positive, then the minimal nature of n is contradicted. So R is equal to 0 and hence, but if R is 0, that means n divides order of G. So this completes the solution. Then 62. Compute the orders of the following groups. Parts are there. In part A we have these groups U3, U4 and U12. In part B we have U5, U7 and U35. In part C we have U4, U5, U20. In part D we have U3, U5, and U15. On the basis of your answers, make a conjecture about the relationship among these orders. Make a conjecture about the relationship among order of UR, order of US and order of URS. Since finding out this, determining the groups and deciding their orders is a routine task, so I'm just simply going to write the orders down and then we will make this conjecture. And the orders are like this. Order of U3 is 2, order of U4 is also 2, and order of U12 is 4. B, order of U5 is 4, order of U7 is 6, this is 24. C, order of U4 is 2, that of U5 is 4, and the order of U20 turns out to be equal to 8. D, order of U3 is 2, order of U5 is 4, and order of U15 is 8. Okay, so now we conjecture based on only these 4 cases that order of URS is equal to order of UR times order of US. We will see in an exercise that is to come soon that this conjecture in this form is actually false. We have to supply some additional hypothesis for this to make this true. But anyway, let's move on. So then exercise. From these examples, we see that we just have to multiply the orders. 63. Let R star be the group of non-zero real numbers under multiplication. Let be the group of non-zero real numbers under multiplication, and let H be the subset of R star such that X square is rational. Prove that H is a subgroup of R star. Can the exponent 2 be replaced by any positive integer? And still have H. Be a subgroup. Okay. So we are considering the set of those non-zero real numbers whose squares are rational. Note that one belongs to H because 1 square is 1, which is rational, and moreover 1 is a non-zero real number. So that H is a non-empty subset of R star. Okay. Let X and Y belong to H. Then X square and Y square are both rational. Hence, xy whole square, which is nothing but x square times y square, is also rational because we are multiplying two rational numbers, so the product is again a rational number. So this implies xy belongs to H. One more thing is that since x and y are non-zero real numbers, so their product is also a non-zero real number, so that means xy will belong to H. Also, x inverse whole square is 1 over x square, and since x is x is a non-zero real number such that x square is rational, so x square is also non-zero, so its reciprocal is again a non-zero real number which is rational, which implies x inverse belongs to H. Hence, H is a subgroup of R star under multiplication, of course. Now, the next part asks us to decide whether this exponent 2 in the definition of H can be replaced by any positive integer, and we see that yes, it can be, because in these arguments we have not used any, we have not used the fact that 2 has a specific value. The entire argument, all the steps also follow if you replace 2 by, say, for example, 3 or 4, or in fact any other positive integer. So yes, you can. The above arguments show that H star, which we defined like this, x belonging to R star such that x to the power n is rational, is also a subgroup. For any positive integer n. So this completes the solution. Then 64. Compute the order of U4, the order of U10, and the order of U40, like that one, exercise 62. Do this group provide a counter example to your answer. To exercise 62. We have order of U. For this we already have seen, it's 2. Order of U10 is 4. Order of U10 is 4. Is it? 2, 5. Okay, so 1. That means what are the positive integers less than 10 and relatively prime to 10? 1, 3, 4, 5, 6, 7, 8, 9. Yes, it is 4. So these are the positive integers. In fact, this is U10. So its order is 4. And what is the order of U40? One can calculate that its order is equal to 4 again. Okay, with that high a value of n, the order is again. Let me just see whether this is actually true. I have written it 4, but is it true? One thing we can do, instead of actually finding the integers less than 40 and relatively prime to 40, is to find their number using that Euler's phi function from number theory. So the prime factors of 40 are 2 and 5. 1 minus 1 over 2 times 1 minus 1 over 5. So this gives us what? 1 over 2 times 4 over 5. Now what have I written here? How can it be 4? That's what I was thinking. It is 16. Okay, since I have spotted a mistake, let me just actually find the integers, because now there is confusion. Although this is the formula for calculating the order, but still let's just find all the elements in the group U40. So the integers less than 40 and relatively prime to 40. So we have to, since 2 and 5 are the prime factors of 40, we have to avoid multiples of 2 and or 5. So 1 anyway comes 3. we have to avoid 2. That means all the even integers have to be avoided. 5, 6, 7, 9, 11, 13, 14, 15, 16, 17, 18. 18 cannot be considered. 19, okay, 21, 23, 25, 27, 29, 31, 33, 35 cannot be taken, 37, 39. Okay, so how many have we listed? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, so the number is 16. Okay, so now we are sure of the number. So here we can see that if we unlike the case in exercise 62 or its answer, where we conjectured that just simply multiplying the orders of these two things we get the order of this higher or bigger group, that is not necessarily true, because here that formula would give us 8, whereas the actual answer is 16. Oh, I have not completed this. No? If so, revise your conjecture. Okay, how can we revise it? By looking at the cases in exercise 62. For example, in part A we had this: U3 is 2, U4 has 2 elements, and U12 had 4 elements. Note that 3 and 4 are relatively prime. Same is the case with the other parts. There, the first two integers from which the UN groups are coming, they are relatively prime, and the orders were multiplied to get the order of the large group. However, here 4 and 10 are not relatively prime. Okay, but what is this order? What is the greatest common divisor of 4 and 10? 2. Okay, so this is equal to 2. Since I made a mistake here, revising the conjecture has also changed. So what I thought is true is actually not true. We have to somehow think of how this 16 is coming from 4 and 2. Let me try to come up with something. So the GCD is 2. Okay. What is the LCM? LCM is the product of the two integers divided by GCD. That is something else entirely. It's not 16, so it won't come from GCD and LCM in that way. Okay. can we guess the order from the elements, from the structure of the elements? How do the elements look? Okay, if we think of it in this way, what are the elements in U4? The elements in U4 are integers less than 4 and relatively prime to 4. That means GCD of A and 4 is equal to 1. The elements in U10 are integers less than 10, positive integers of course, and relatively prime to 10. Okay, and the ones in U40 are less than 40 and relatively prime to 40. Hmm. 16. How can 16 come from 2 and 4? Of course 4 square is 16, but that is not what we are, I mean that does not have any explanation why we have to raise 4 to the second power. Now at the moment I cannot think of any way how this 16 is coming from 2 and 4. So it has to be left here. This solution remains incomplete. Of course, I would ask you to think of something. At the same time, I will also think of it. And when I come up with how this 16 is coming from 2 and 4, I will let you know. Okay, so let's go to the next exercise. So the next one is 64. Now I already have dealt with 64. This is 65. Find a cyclic subgroup of order 4. Find a cyclic subgroup of order 4 in U40, and the solution is of course if you search for such a subgroup, you will see at one point that this is one such subgroup. The cyclic subgroup generated by 7. It has these 4 elements: 1, 7, 7 square, which is 9, 7 and 7 cube, which is 23. In U40, 7 to the power 4 is the same as 1. Okay, so that means the order of 7 is 4, and that's why the cyclic subgroup generated by 7 has only 4 elements. Exercise 66. Find a non-cyclic subgroup. Of order 4 in U40. Excuse me. such a subgroup is this 1, 11, 29, 39. To see that this is a subgroup, you just have to verify that this set is closed under the product we have in U40. And also this is not cyclic because no element in this subgroup has order 4. That we have to mention. This subgroup is not cyclic because it has no element of order 4. Exercise 67. Let G be the set of matrices, 2 by 2 matrices, where the entries are all integers under addition, that is addition of 2 by 2 matrices. Let H be the set of those matrices A, B, C, D in G such that the sum of all of their entries are equal to 0. Prove that H is a subgroup of G. Okay, what else? What if 0 is replaced by 1? That means here, if this 0 is replaced by 1, what happens? Does it remain a subgroup or it does not become a subgroup? We have to decide that. We have clearly, if all the entries of such a matrix are equal to 0, then the sum of the entries is also 0. That means the 2 by 2 0 matrix belongs to H, so that H is a non-empty subset of G. Let A, B, C, D and E, F, G, H belong to H. This means that all these entries are in each of these two matrices, all the entries are integers. Now, if you take the difference of these two matrices, then it will become A minus E, B minus F, C minus G, and D minus H. And clearly this again belongs to H, because it is a 2 by 2 matrix where again all the entries are integers, because these are differences of integers. Hence H is a subgroup of G. Now if we replace this 0 by 1, then it will not become a subgroup, because the additive identity will not belong to H then. The subset H star of all the matrices A, B, C, D belonging to G such that the sum of the entries is 1 is not a subgroup of G, because the additive identity does not belong to H star. So that is why it will not be a subgroup anymore. Then exercise 68. Let, I need ink. Let H be the subset of the general linear group. It is the set of all A belonging to GL2, R. The general linear group of non-singular 2 by 2 real matrices under matrix multiplication, where determinant of A is an integer power of 2. Okay. Show that H is a subgroup of the general linear group. So first we have to see that H is non-empty. Note that the determinant of the 2 by 2 identity matrix, where these 1, 0, these are real numbers, is 1, which is an integer power of 2, and hence this belongs to H. So this proves two things. One is that H is non-empty, and the other is that the identity element in the original group, general linear group, also is in H. Now let A and B be two elements in H. Then determinant of A is 2 to the power m and determinant of B is 2 to the power n for some integers m and n. Now, what about the determinant of a-b inverse? We know from our knowledge on determinants, or it can be easily proved since these are 2 by 2 matrices we are dealing with, that the determinant of a product of two matrices is equal to the product of their determinants. Just like that, the determinant of the inverse of a matrix is the reciprocal of the determinant of the original matrix. So this is 2 to the power m times 2 to the power n to the power minus 1. So this again becomes an integer power of 2. Hence, AP inverse belongs to H. So H is a subgroup of this general linear group. Then 69. Let H be a subgroup of R under addition. Let K be the set of all numbers 2 to the power A, such that A belongs to H. Prove that K is a subgroup of R star under multiplication. Okay. Since 2 to the power a is greater than 0 for all real numbers a, we have K contained in R star. Okay, so no element of K can be 0. All the elements are not only not equal to 0, but they are positive. Also, since okay, so H is given to be a subgroup of R under addition. So H must contain the identity element 0. Since 0 belongs to H, we have 1 equal to 2 to the power 0 belonging to K. This shows that K is a non-empty subset of R star, and hence K is non-empty. Let 2 to the power A and 2 to the power B belong to K, where A and B belong to H. Then, since H is an additive subgroup of R, so A minus B belongs to H, and so 2 to the power A times 2 to the power B inverse. By the rules of exponent, this becomes equal to 2 to the power A minus B, ordinary rules of exponent that we have in the system of real numbers. Okay, so we can write it like this, and then by the definition of the set K, this belongs to K. So that's it. We have taken two elements in K, and this product belongs to K. So K is a subgroup of R star, that is non-zero real numbers under multiplication. This completes the solution. Next, 70. Let G be a group of functions from the set of real numbers to the set of non-zero real numbers, where The operation on G is multiplication of functions. Multiplication means ordinary multiplication of real valued functions. Let H be the set of those functions f in G such that the value of f at 2 is 1. Prove that H is a subgroup of G. Can 2 be replaced by any real number? This 2. Okay. Let's not denote it by I. Let us denote this function by f itself. Let f be the function from R to R star B defined by f of R equal to 1 for all R belonging to R. Clearly this function is in G because it is such a function whose domain is R and this set is R star, the set of all non-zero real numbers, and it is the constant function that maps all the real numbers onto the fixed non-zero real number 1. Okay. Then f belongs to G such that in particular if you take R equal to 2, that there also the value is 1. Thus this f belongs to H and hence H is non-empty. So H is a non-empty subset of G. So let us now take two elements in H. Let G and H belong to G. Then G and H are functions from, both of them are functions from R to R star such that G of 2 is 1 and H of 2 is also equal to 1. Now, what about G divided by H? In this case, divided by, because the binary operation in this group is multiplication of functions, not composition of functions. Okay. Now G divided by H is a function from R to R. It will be a function from R to R star because these are after all elements in the original group G. So you can form the product GH inverse, which in this particular case, in our case, looks like this, such that, note that in particular we can divide by the function H because all the values of H, just like G, are non-zero real numbers. So when we are calculating this quotient at some point, that both G and H will be evaluated at that point, and the corresponding quotient of those real numbers will be formed. There the denominator never becomes 0. So that's why we are able to do this, and that is why we are in fact considering the second set to be the set of non-zero real numbers, such that G by H evaluated at 2 is G of 2 divided by H of 2 is equal to 1. This implies G by H belongs to H. Is it H? Yes, it is H. Hence, H is a subgroup of G. Just like many of the previous exercises, in this case also 2 can be replaced by any real number actually. 1, however, there will be problem if we replace. Can you replace 1 by something else? No, because then the identity element of this particular group G, which is this constant function actually, will not belong to the corresponding set. Anyway, we can replace 2 by any real number. And the resulting subset of G will still be a subgroup of G. Then exercise 71. Let G be the set of, okay, so G is the general linear group GL2, R, and H be the set of all matrices like this, that is diagonal matrices, where A and B are non-zero integers. Oh, so A and B have to be non-zero but integers additionally. Okay, fine. Under the operation of matrix multiplication. Non-zeroness of both A and B that is needed to make this matrix non-singular, so that it is an element here. But additionally, now A and B are required to be integers also, not just any real numbers. The operation of matrix multiplication. Prove or disprove that H is a subgroup of G. Interestingly, this will not be a subgroup because inverses will not necessarily exist. Let us see what we mean by that. Note that this is a matrix where A and B are integers. Both of them are equal to 2, so non-zero. So that means this belongs to H, but its inverse in this group, it belongs to H means it belongs to the general linear group also, so its inverse will exist, and one can verify that this inverse is nothing but this, which again is a non-singular matrix having real number entries, but these are no longer integers. So that's why this does not belong to H. So H is not a subgroup of G, this G. Let H be the set of all numbers, a complex numbers a plus bi, where a and b are real and the product ab is non-negative. Prove or disprove that H is a subgroup of the set of complex numbers, or rather the group of complex numbers under addition. This also, like the previous one, will not be a subgroup. Let us see why. So AB has to be non-negative. Besides that, there is no other restriction. A and B just have to be real numbers. Note that 1 plus 2i and 2 plus I belong to H, because in both the complex numbers the real and imaginary parts are positive, so their products are also positive. But 1 plus 2i times 2, oh not times, sorry, we are dealing with addition, minus 2 plus I becomes what? 1 minus 2, this is minus, is minus 1, 2i minus I is I, and this does not belong to H, because if you multiply the real part minus 1 and the imaginary part 1, you get minus 1, which is not non-negative, it is negative. So H is not a subgroup of C under addition. Next, (73). Shall we be able to complete it today? Let's try. Let another H, let H be the set of all complex numbers a plus bi, where a and b are real, and a square plus b square is equal to 1. Prove or disprove that H is a subgroup of C star. That is non-zero complex numbers under multiplication of complex numbers. Describe the elements of H geometrically. Okay, this will be a subgroup. Note that the complex number 1, every real number is a complex number. So 1 is a complex number and it belongs to H, because the real part is 1, imaginary part is 0. 1 square plus 0 square is 1. So that H is non-empty. Also, zero does not belong to H clearly, because 0 square plus 0 square is 0, not 1. So that H is actually a subset of the set of non-zero complex numbers. Now let a plus bi and c plus di belong to H. Then a square plus b square is 1 and c square plus d square is also 1. Now a plus bi times c plus di becomes ac minus bd plus ad plus bc times I. And if we take the sum of the squares of the real and imaginary part of this complex number, then one can show that this becomes equal to this. I leave the details of this calculation to you. You have to make sure that we do get this thing, that this square becomes equal to the product of these two things. So this is equal to 1. This implies a plus bi times c plus di belongs to h. Also 1 over a plus bi equal to, and if you take the sum of squares of the real and imaginary parts of this complex number, then you get plus minus b over a square plus b square whole square. If you calculate a little bit, you will end up with 1 over a square plus b square. So this is again 1. This proves that 1 over a plus bi belongs to h. Hence h is a subgroup of C star under multiplication. Now lastly, the geometry of this, I should not say geometry but rather geometric representation of the elements of this group. The elements of H are the points on the unit circle in the complex plane. That is, geometrically they are points lying on the circle in the complex plane whose radius is 1 and whose center is at the complex number z equal to 0. That is the one which looks like this, where this radius is 1. This is the real axis, this is the imaginary axis. Okay. Then exercise 74. Let G be a finite abelian group and let A and B belong to G, prove that the set denoted with this symbol and is defined to be the set of all elements of the form a to the power I times b to the power j, where I and j are integers, is a subgroup of G. What can you say about the order of this subgroup in terms of the orders of these elements? Excuse me, let me just check one thing. Okay. So first of all, we have to prove that this is a subgroup of G. Clearly it is non-empty. So we can start by directly taking elements from it. Let this belong to A comma B, where I1, I2, or let's just maintain the order I1, J1, I2, J2, these are integers. Then because we are in an abelian group, so we don't have to really bother about the order. Using the rules of exponent, we can write it as a to the power minus I2, b to the power minus j2, and because of that, we don't have to bother about the order. We can write the elements in any order we want. Because of that fact, we also have this. Actually, there is one more step before this. We have to bring the powers of A together and the powers of B together. Then after that we have this again by the rule of exponent. But you understand what I have done here. So this again is an element of that form where I1 minus I2 and J1 minus J2 are integers. So this belongs to A comma B. Hence this is a subgroup of G. Now the next part asks us this: what can we say about the order of this subgroup? Being a subgroup of a finite group, this is also a finite group, so it will have a finite order, and the elements A and B, being elements in a finite group, they themselves have finite orders. So what is the relationship between these things? We can easily give one relationship, which actually are some bounds for this number, but a sharper and more accurate relationship is given in terms of divisibility, which however we cannot prove at this moment, or at least I don't know any way of proving it without using Lagrange's theorem, which we have not got yet. So we have to be content with only the bound. Since the cyclic subgroup generated by A, it consists of all the integral powers of A, which automatically are elements of this form where this J is 0. So that's why this is a subset of this, and just like that, this is also a subset of this. So we have maximum of the order of A and the order of B. Order of A is nothing but the order of the cyclic subgroup generated by A. That is this. Like that, order of B is the order of the cyclic subgroup generated by B. This will be less than or equal to the order of this subgroup. Now, define the function, say K, from the Cartesian product of the cyclic subgroups. This is not a group. I mean, one can show that this is a group, but that is not the point here. This is ordinary Cartesian product of two sets which happen to be cyclic subgroups into this by defining K of an element in this Cartesian product will look like an ordered pair, where the first coordinate is an element from here, that is a to the power I, where I is some integer, and the second coordinate is an integral power of b, and we are mapping that onto this. Okay, clearly K is well defined as a mapping, and because of the existence of such a mapping, this set will have at least as many elements as this set. You see, when you define a mapping from one set to another set, say A is a set and B is another set, and say you define a mapping F, then A has at least as many elements as B, provided this mapping is onto, okay, which in this case it is. I forgot to mention that ontoness, but once you have the fact that this mapping is onto, then A has at least as many elements as B. A will have more elements than B if the mapping is at the same time not one-to-one. Okay, in that case you will have things like this, so that for a single element of B you may have more than one element in A. or you will have more than one element in A if the mapping F is not 1 to 1. But ontoness of the mapping tells us that for every element in B, there is at least one element in A. Okay, so we have to mention that ontoness. This is well defined and onto. We write like that. And onto. Hence, the number of elements in the second set is less than or equal to the number of elements in this set. Which is nothing but this product. Thus, we have these bounds. Okay, that much we can say, we can show. A sharper relationship is this. The LCM of these two things divides the order of this group, and the order of this group divides the product of these two orders. This we cannot prove at present. Okay, so here the solution ends. Then 75. Next 75. Let H be a subgroup of a group G . Prove that H Z G, which is by definition the set of all elements H Z where H belongs to H and Z belongs to Z G, is a subgroup of G. Okay, clearly the set is non-empty because both H and the center of G are non-empty. So we start by taking elements in it. Let H1Z1 and H2Z2 belong to HZG, where let this be the last exercise in this video, because I don't think I will be able to complete all of them. There is no point rushing through them just for the sake of finishing them in one video. So let's make this one the last, and in the next one in the next part we will complete, because the total number of exercises in this set is 80, where H1 and H2 are in H, and Z1 and Z2 are central elements, are in the center of the group. Then H1 Z1, H2 Z2 inverse is equal to H1 Z1, Z2 inverse, H2 inverse. Keep in mind that now it's not given that the group is abelian. So if we want to take inverses inside, we have to change the order. And this is equal to H1 H2 inverse, Z1 Z2 inverse, because Z1 Z2 inverse is in Z of G. Why? Because the center of a group is itself a subgroup. So since Z1 and Z2 are central elements, so Z1 Z2 inverse is also a central element, and because of that this Z1 Z2 inverse commutes with every element of G. In particular, it commutes with H2 inverse. So in place of Z1 Z2 inverse, H2 inverse, we have written H2 inverse Z1 Z2 inverse. Also H1 H2 inverse belongs to H, because H is given to be a subgroup of G, and H1 and H2 belong to H. So we have got this product in this form, where this is an element of H and this is an element of ZG. Thus hence this is a subgroup of G. Okay, so let's end the video here. If you want to say something, you can comment in the comment section below. So that will be all in Gallian's exercises tonight. Until the next video, it's me, Lucifer, from a mathematical room. Have a nice night.